All right, if you're managing a serious boiler system, you already know that just following best practices isn't going to cut it anymore, right? To find those major savings, you need cold, hard numbers. So in this explainer, we're going to build out the expert's mathematical toolkit. We're moving past the guesswork and getting into rigorous quantitative results. So here's the game plan. We'll kick things off by setting the stage. Then we'll dive right into the equations for core efficiency, quantifying your losses, modeling your potential savings, and we'll wrap it all up by putting these tools into a real strategic context. So let's just get this out of the way first. Why are we so obsessed with the numbers? Because honestly, it's what separates a good manager from a truly great analyst. This is all about having that solid mathematical framework to diagnose, to optimize, and maybe most importantly, to justify every single improvement you want to make. Okay, let's get into it. First up, our core efficiency equations. These are the absolute fundamentals for figuring out how your system is performing right now, your baseline. So when it comes to measuring boiler efficiency, ASME basically points to two main paths. You've got the direct method, which is super straightforward, what goes in versus what comes out. Then there's the heat loss method. Now, the direct method is simpler, for sure, but the heat loss method, that's usually where the real accuracy is. And here's why. Think about it. If your measurement is off by 1% on a tiny little heat loss, it's not a big deal. But a 1% error on your entire fuel input, whoa, that's a massive problem. So yeah, your choice depends on what gear you have, but if you want a really surgical view of what's happening, the heat loss method is often the way to go. So here it is, the direct method in all its glory. This equation gives you that one big top-line number. It's like the classic black box approach, you know? You're basically asking, for all the energy I poured into this thing, how much useful energy, in the form of steam, actually came out the other side? But, and this is a big but, that simplicity can really bite you. You're measuring these huge energy flows, right? So even a tiny little error in your steam flow meter or your fuel's heating value, it gets blown way out of proportion. It completely skews your final efficiency number. So the takeaway here is, if you're going to use this method, your instrumentation has to be absolutely top-notch. It's not a nice to have, it's everything. And then there's the heat loss method, which, I love this, it totally flips the script. Instead of focusing on what you got right, you become a detective for what went wrong. You hunt down and account for every single BTU that escaped, whether it went up the stack, radiated through the boiler walls, whatever. What you're left with is basically a treasure map, a diagnostic roadmap showing you exactly where to make improvements. All right, so let's start filling out that diagnostic toolkit. These next few formulas are all about pinpointing exactly where your energy and your money is leaking away. First on the list is the secret formula. Now, this thing is a must-have tool for when you're out in the field. It lets you quickly estimate your thermal efficiency just by analyzing flue gas loss. And that's huge because flue gas is almost always the #1 place you're losing energy in a boiler. And the beauty of this formula is just how practical it is. You grab a standard flue gas analyzer, plug in a couple of constants for whatever fuel you're using, and bam, you can diagnose your combustion efficiency right there on the spot. It gives you a number you can act on, like, right now. Okay, next up in the toolkit, Grashof's formula. This one is all about putting a price tag on one of the biggest money pits in any steam system: leaks. I mean, this formula is what takes you from saying, oh, looks like we have a leak over there, to that leak is hemorrhaging X kilograms of steam every single hour. See, this is how you turn a simple visual inspection, or maybe an ultrasonic one, into a hard number, a quantifiable mass flow rate of steam that's just vanishing into thin air. And once you have that data, well, now you can calculate the actual financial hit and figure out which leaks you need to fix first to get the biggest bang for your buck. Okay, so we've got tools to measure and diagnose. Now let's switch gears and look at the project tools. These are the equations that help you quantify just how much you could save, and more importantly, help you justify spending the money to do it. This next one, this equation is absolutely critical. It's for sizing up one of the biggest, and I mean biggest, heat recovery opportunities out there: flash steam. It tells you exactly what percentage of your hot, high-pressure condensate is going to literally flash back into usable, low-pressure steam when the pressure drops. This stuff isn't waste, people. It's a valuable resource hiding in plain sight. And all you have to do is look up a few enthalpy values from a standard steam table, plug them in, and you can model this source of basically free energy with incredible precision. I'm telling you, this calculation right here, it's the absolute foundation for making the business case for any flash steam recovery project. And here's a perfect example of where you'd use it. This four-step process is how you'd figure out the maximum energy you can possibly squeeze out of your boiler blowdown, which is another one of those continuous waste streams that people just forget about. You see, first you capture the really valuable high-grade energy as flash steam. Then you go after the lower-grade heat that's left over in the hot water. It's a 1-2 punch. Now, let's look outside the boiler room for a second, because there are massive savings hiding in your auxiliary systems. I'm talking pumps, fans, you name it. Let's say you put a VFD, a variable frequency drive, on one of them, and you slow it down by just 10%. Doesn't sound like a huge deal, right? Well, you would be wrong. The impact is absolutely massive. It's all thanks to something called the affinity laws. The key thing to know is that power draw is tied to the cube of the speed. So that tiny little 10% reduction in speed, it slashes your power consumption by a whopping 27%. That is a total game changer when you're trying to get a VFD retrofit approved. Okay, last section. Let's zoom out a bit. We need to connect all these nitty-gritty calculations to the high-level strategy you're using to run your energy programs. This is where the rubber meets the road, where your numbers turn into a rock-solid business case. Think about it. Every single equation we've talked about plugs directly into these bigger picture concepts. That savings number you calculated for a blowdown heat recovery project, that becomes the cornerstone of your life cycle cost analysis. That steam leak mass flow you got from Grashof's formula, that's the hard data you use to calculate the net present value and get that repair project greenlit. It all connects. So really, what's the big takeaway here? It's that mastering these details, getting comfortable with the math, is what takes you to the next level. It's the difference between just managing a system and actually engineering its performance. This is how you find and deliver those huge, high-impact results that get you noticed. So I'll leave you with this question to chew on. Looking at this toolkit, which one of these equations are you going to use to find your next big win? The tools are all here. It's time to stop estimating and start engineering. Now go find those savings.